In part 3 of limits and continuity, we do some tricky limit calculations, applications of the squeeze theorem, and at the end, an epsilon-delta proof. We start with using algebra to find some limits for 3 cases, where in each case you see square roots involved. Now, in these kinds of problems, it is often the best technique, maybe not always, but often, to try to rationalize either the denominator, as in part A, or even the numerator, as in parts B and C. I'm going to show you a second way to do part A that's actually a little quicker, but let me also show you how to rationalize the denominator in this case. What you want to do is you want to multiply this fraction by a disguised form of 1 so that it doesn't change the function. And in that disguised form of 1, you make the top and the bottom the same. You want to pick it so that it is what you might call the conjugate of the bottom here with the square root, which means you take the first expression, the square root of x, and then you change the sign of this minus sign to a plus sign. If it had been a plus sign, then you change this to a minus sign. If you do it to the bottom, you've got to do it to the top as well, so again, you don't change the function. And that's going to make it look more complicated, it seems, at least on the top. But on the bottom, something kind of magical happens when you multiply these two binomials, when you FOIL, first times first, outside times outside, inside times inside, and last times last. The outside and inside terms cancel. That's the magic of it. Think about it. You'd have a 3 times square root of x and a negative 3 times square root of x from those two terms. Square root of x times square root of x, that's nice as well. That's just x. And then negative 3 times positive 3, that's minus 9. And look, isn't that kind of magical as well? That's going to cancel with the x minus 9 on the top. It's going to divide out to give you a 1, not 0, it gives you a 1, and you end up with the limit as x approaches 9 of something fairly simple. In fact, a continuous function of x near x equals 9. We can now evaluate this limit by just substituting 9. We couldn't do that back here because we'd be dividing by 0. We can just get square root of 9 plus 3, which is 3 plus 3, and the answer is 6. Let me show you a second way to do part A, and that is to do a substitution. You might say let t equal square root of x so that t squared equals x. And you could also say, again, we're thinking about part A here, that as x approaches 9, since square root of 9 is 3, that's equivalent to t approaching square root of 9, which is 3. X approaching 9 is equivalent to t approaching 3. So we can change the limit in part A to look like this. The limit as t approaches 3 of x gets replaced by t squared, and square root of x gets replaced by t. And then this is simple because you can factor the top as t minus 3 times t plus 3 and divide out the t minus 3 with the bottom to give you, again, a 1. And we get the same ending answer as before. 3 plus 3 is 6. Okay, so that's a little quicker way to do it. All right, you don't have to bother with this rationalizing the denominator in the first example. All right, on to part B. Limit as h goes to 0 of square root of 25 plus h minus 5 all over h. Once again, you can't plug in the value of h equals 0 in this case because you'd be dividing by 0. We need some other technique. Once again, we get a square root involved. Once again, rationalizing, in this case, the numerator will be useful with this multiplication of the top and the bottom by the conjugate of the thing involving the square root. That's a mouthful. And that probably is the best way to do this one. There might be another way, but that seems like the simplest approach to me. This kind of limit in B and in fact in C come up in derivatives. We're going to be doing videos about derivatives very soon here. I want to multiply the top and the bottom by the conjugate of the top in this case, the numerator, 25 plus square root of 25 plus h plus 5. Change that minus sign to a plus. If I do it to the top, I've got to do it to the bottom. And then the top will simplify nicely. The square roots will go away. They won't go away in the bottom, but that's okay. Let's see what happens when I FOIL out the top. First times first. The square roots go away. I get 25 plus h. The outside products and inside products cancel. That is, again, the magic of multiplying by the conjugate. And then last times last is minus 25. Already you can see nice looking kinds of things are going to happen here. You can cancel those 25s. 25 minus 25 is 0. That's a 0. You're left with an h on the top. You can divide that h out after canceling the 25s with the h on the bottom to give a 1. So you'd have a 1 on the top. Limit as h goes to 0 of 1 over the h on the bottom went away. Square root of 25 plus h plus 5. There's no problem now plugging in 0. This is a continuous function of h near 0. I can evaluate this limit by just plugging in 0. I get 1 over square root of 25 plus 5, which is 1 over 5 plus 5, which is 1/10 or 0.1. Okay, so that's the answer for part B. And again, this is related to derivatives. If you know something about derivatives and using limits to evaluate derivatives, these kinds of things should look familiar. All right, finally on to part C. Evaluate this crazy looking limit where we've got fractions within fractions in addition to square roots. All right, let's go ahead and write it down here. I think in this case, it might be better to not do the rationalizing first. It might be better to get rid of the fractions within fractions. And so what I'm going to do first is multiply by a disguised form of 1 that will get rid of the denominators in these fractions. 4 times the square root of 16 plus h. So I'm not rationalizing here. I'm trying to get rid of fractions within fractions. If I do it to the top, I've got to do it to the bottom. You also could, instead of doing what I'm doing, you could get a common denominator to subtract those fractions and think of 1 over, as dividing by h as multiplying by 1 over h. That's another way to do it. When you multiply this through here, this times this, the square root of 16 plus h's will cancel. You'll be left with a 4. And then minus 1/4 times this, the 4's will cancel. You'll be left with square root of 16 plus h. And just leave the bottom as is. Now do your rationalizing. Multiply the top and the bottom by 4 plus the square root of 16 plus h. Do it to the top. I've got to do it to the bottom. Again, the bottom's going to look pretty complicated, but this is going to give us the right answer in the end. Multiply out the top, FOIL. We get 4 times 4 is 16. Outside and inside products cancel. Last times last. The square roots go away with a negative sign. Be careful about using parentheses like I'm doing here. And yeah, it's a nasty looking bottom of this fraction, but that's okay. Don't panic. Distribute the minus sign through. The 16s will cancel. You'll be left with a negative h up top. Negative h cancels with the h on the bottom to leave you with a negative 1 up top. This h in the bottom goes away. We are now left with a function of h that is continuous near h equals 0. You can evaluate this limit by plugging in h equals 0. Get negative 1 over 4 times the square root of 16 times in parentheses 4 plus the square root of 16. When you plug in h equals 0, the square root of 16 is 4. This product here is 4 times 4, which is 16. That's 4 plus 4, which is 8. Looks like the answer is negative 1 over 16 times 8 is 128. And I did check all these ahead of time. That is the correct answer. Problem 2 involves a cube root instead of a square root. Is there some sort of analogous technique like rationalizing like we did with the conjugate in number 1? Well, there are techniques, but we're going to use some directions here. We're going to use a substitution like we did in the second technique for part A in number 1. We're going to let t equal the cube root of x to help us compute this limit. Notice we cannot plug in 8 in this limit because we'd be dividing by 0. By the way, dividing by 0 often leads to limits not existing, leads to what you might call vertical asymptotes if you graph the function. If the top goes to 0, though, as x goes to 8, which it does because cube root of 8 is 2, then you don't necessarily have a vertical asymptote for the graph of this function. You have what might be called a removable discontinuity that can be removed by redefining the function essentially at x equal 8 to be whatever this limit happens to equal. We're sort of implicitly assuming this limit exists. So t is cube root of x, so that's equivalent to t cubed equaling x. And it's also equivalent to x approaching 8 being the same as, I've got lots of equivalencies here, as t approaching cube root of 8, which is 2. Okay? So we can change this limit to a limit as t approaches 2, replace the cube root of x with t, replace x with t cubed. Now, this still doesn't look super easy because you got a cube there. However, this is something worth knowing for algebra problems like this, or calculus problems where you use algebra like this. When you have the difference, or sum in fact, of two cubes, t cubed and 8 is 2 cubed, and actually the 8 is a nice cube, but it, even if this were a 10 or something, technically that's a cube as well. It's the cube root of 10, which is not a nice number, but it still is technically a cube. But 8 is a nice cube, it's 2 cubed. When you get the difference or sum of two cubes, you can always factor it as a certain binomial times a certain trinomial. Binomial has 2 terms, trinomial is going to have 3 terms. And with the difference of 2 cubes, you want to put the first expression that's being cubed first here, minus the second expression, the cube root of the second expression, which is 2 here in the second spot. And then for the trinomial, you want to have, in this case, the t squared plus this 2 times t plus, not minus, plus the 2 squared, which is 4. That's the formula for the difference of 2 cubes. I'm going to write it down in general. It's often written a cubed minus b cubed is a minus b times a squared plus ab plus b squared. No 2 there. That's just an ab. It's sort of tempting to think you want a 2 there or something. You can always check this by expanding it out. Multiply a, the first term there, times everything. I'll get a cubed plus a squared b plus ab squared. I multiplied a times each term. Now multiply negative b times each term. That gives me negative a squared b minus ab squared, negative b times ab, and then minus b cubed. This cancels with this cancels with this. You're left with a cubed minus b cubed. And a similar thing can be done if you change this minus sign to a plus sign, so you have the sum of 2 cubes. Then you would end up changing this to a plus sign and this to a minus sign. You can check that it works. Anyway, because of that, we now have expressions that can be divided out to give you a 1. And it's now the limit as t goes to 2 of 1 over t squared plus 2t plus 4. And this rational function is continuous near t equals 2. In fact, at t equals 2, you can now evaluate the limit by substitution. Each of those terms on the bottom is now 4. 4 plus 4 plus 4 is 12. The answer is 1/12 right there. Number 3 involves a couple applications of the squeeze theorem. Part A, it's abstract. We don't specify what f of x is. We want to find its limit. Part B, it is a limit of a particular function. Let's think about part A first. Let's think about the squeeze theorem graphically, intuitively, and then I will go ahead and write the theorem itself down. So what we want to do is, well, you could use your technology to graph these two functions here and here. I will go ahead and just graph them without technology. 5 cosine of 2x. Okay, so that's a cosine wave which is going to start at its peak when x equals 0 in this case. That peak will be the value of 5 because the amplitude of the cosine wave is 5 here. It's going to be a graph looking like this. Its period is going to be 2 pi over 2, which is just pi, so it's going to be back up here when you're up to pi. And then it's going to be periodic. It's going to continue forever and ever in both directions. So that's 5 cosine of 2x. What about 3x squared plus 5? That's a quadratic. Its graph is a parabola. opening upward because the coefficient of x squared is positive. Y-intercept of 5. It's going to touch the cosine graph here, the 5 cos 2x graph right there. When x equals 0, it'll look about like this. Okay, so that's this graph right there. And this one is this graph. You're told f of x always has a graph that's between these other two graphs. 5 cosine of 2x is less than or equal to f of x is less than or equal to 3x squared for all x. It's always between them. You have no idea what f of x looks like other than to say its graph is between the red and green graphs here. It could be some crazy looking graph, but it's between them. And therefore, near 0, it's squeezed toward the same limiting value of 5. The answer has got to be 5 by the squeeze theorem. All right, let's be a little bit more official about it. What does the squeeze theorem say? Squeeze theorem. In the context where we need to use the squeeze theorem, there are other versions of this, like as x goes to infinity, for example. Suppose we've got 3 functions. F, g, and h are all defined on some possibly small open interval near some number called the number c. Are all defined on some open interval containing the number x equals c. So f, g, and h are functions. C is a number, okay? Also suppose f of x is less than or equal to g of x is less than or equal to h of x, set up kind of like this, except g is playing the role that f did up here. For all x near x equals c, in other words, in the open interval near c. And the limit as x approaches c of f of x and the limit as x approaches c of h of x exist and are equal to each other. The conclusion is then the limit of the middle function that's stuck between them must equal this same number. We should give this number a name. Let's call this number L. Then the limit as x approaches c of g of x also equals L. So in our problem here, excuse me, in our problem here, this is playing the role of f of x, this is g of x, this is h of x. Sorry that I probably should have used an f of x in the middle and a g of x there. Anyway, you get the idea. I'm not going to write out a proof using the squeeze theorem. I'm just going to describe it. You would say, hey, we've got these functions that are all defined for the entire real number line for all x, and we're assuming this is true, and we know that the limit of this one as x goes to 0, the c is 0 here, and the limit of this one as x goes to 0, both exist and in fact are 5. Therefore, the limit of f of x is also 5 as x goes to 0. So the answer is 5. Because of that, I just gave a verbal proof. If you want, you could take the time to write down what I said, and you'd be applying the squeeze theorem to do that proof. Part B, find the limit of a particular function, x squared times sine of 1 over x. Now, I think it was a couple videos ago, I showed the graph of just plain sine of 1 over x, which was a crazy graph, a crazy function that oscillates infinitely often between -1 and 1, in fact, near 0. So that's still involved here, but I'm multiplying it times x squared. The x squared is not going to affect the fact that it oscillates infinitely often. If I try to graph this function here in part B, and you can use technology if you like, you will still see oscillations that are infinitely often near 0. However, those oscillations will be getting smaller and smaller, so it oscillates really, really fast as you approach 0. In fact, there are infinitely many oscillations here. But the oscillations do get smaller in amplitude the closer you get to 0. And so because of that, intuitively, the limit should be 0. And in fact, that is the answer. Let's be more official about using the squeeze theorem for this problem, okay? Let's be a little bit more careful. Let's let f of x equal x squared times sine of 1 over x. And this is reminding me that I actually can weaken the hypotheses of the squeeze theorem here to also say that f and g, I said they're defined on some open interval containing x equals c. They actually don't have to be defined at c itself. And in this case, f of x is not defined at 0. Now, I could make it a piecewise function to make it defined at 0 if I wanted to, but that's kind of beside the point. I could add except possibly at c. Except possibly, I'm running out of room here, at x equals c is what that says. Except possibly at x equals c can be part of the hypotheses of the squeeze theorem to make it apply to more situations like the situation at hand. It makes it really a stronger theorem because of that. Let's let, what should we let g of x and h of x be? Or actually, if I'm doing the setup here, I should call this g of x, I'm sorry. G of x. What should I let f of x and h of x be? That's not so clear. Well, sine of something is always between -1 and 1. Multiply that something by, in this case, x squared. The product has to be between plus or minus x squared. This graph here is going to be between the graphs of x squared and negative x squared. Y equals x squared and y equals negative x squared. Those are the two graphs that it has to be squeezed between. So let's go ahead and write that down. Let f of x equal the one that g of x is greater than or equal to. That would be negative x squared. And h of x be the one that g of x is less than or equal to. That would be positive x squared. Since sine of 1 over x is between -1 and 1 for all x, where it's defined, which doesn't include 0, we can say that these inequalities are true. F of x is less than or equal to g of x is less than or equal to h of x for all non-zero x as well. Furthermore, f of x and h of x are pretty simple. The limit as x goes to 0 of f of x equals the limit as x goes to 0 of h of x. Both of those limits equal 0. L is 0 as well as c being 0. Therefore, 3 dots means therefore, by the squeeze theorem, the limit that we're interested in of g of x, this is a g here again, as x goes to 0 of g of x, and I'll go ahead and write x squared sine of 1 over x, is also equal to L, which is 0. We're done. QED. So that's a little bit more official way to actually apply the squeeze theorem and not just give an intuitive description of what the answer is. That's a proof right there. Our last problem is a proof with the epsilon-delta definition of a limit. Use the epsilon-delta definition of this equality, the limit as x approaches c of f of x equaling L, to prove a fairly simple limit. So this is really overkill, but it's worth it to get some practice with the definition of a limit. When you have a linear function, it leads to the easiest kinds of proofs, but we still have to wrestle with the definition itself. So let's go ahead and write down the definition here. What is the epsilon-delta definition of this fact? There are some technicalities about assuming f is defined on some open interval containing c, except possibly at the point c. You can state those kinds of things in the preamble of the definition. But if we're dealing with a simple function like a linear function here that's defined everywhere, we don't have to worry about that so much. So let's get at the essence of the definition. Here it is, and I'll just write it down, then I'll explain it. For all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon for all values of x, satisfying, well, leave a little space here, the fact that the absolute value of x minus c is less than delta. And technically, since limits are unaffected in the definition by what happens to the function at c, we also want to include the fact that x doesn't have to equal c here, that the absolute value of x minus c is greater than 0, which means x does not equal c. Another way you can write the last clause here is you can say, i.e., if you know that the absolute value of x minus c is between 0 and delta, that implies, right, by last clause I mean this part here, that implies that the absolute value of f of x minus L is less than epsilon. Now, if you've never seen this before, you're like, whoa, what in the world is this about? The first key thing to realize in trying to understand this is to realize how to geometrically interpret the absolute value of the difference of two numbers, a minus b, which is equal to the absolute value of b minus a, and it represents the distance between a and b. A and b are numbers. Imagine a number line. This is the distance between a and b on a number line. If you've got a number line, whether the number line is horizontal or vertical, it doesn't matter. This quantity, you can try some examples, represents the distance horizontally in this case and vertically in this case between these numbers. So that's really important for understanding this definition. Let's in fact think about it in the context of this example here. So this function here is a linear function of x. It's got a slope of 2 and a y-intercept of -5. Say -5 is right here. Slope is 2, so it goes up by 2 units for every 1 unit increase of x. Let's just draw it. Its graph is a straight line. When x is 3, the function value is indeed 1. 2 times 3 is 6, minus 5 is 1. So when x is 3, let's say 3 is about, let's see, the x-intercept of this is going to be 2.5. So this is 2.5 right there. So let's say 3 is right about here, and the y value there is 1. 3 is playing the role of c. That's f of x. And this is the L in the definition. What are we saying? We're saying for all positive numbers, call it epsilon. It's just tradition to use that Greek letter. No matter how small. Now, you don't see the words no matter how small in there, but that's in your mind. No matter how small, I can make the distance between the function output f of x and L on the y-axis less than that arbitrarily small number, as long as the distance between x and c, x and 3 in this case, on the x-axis is less than a number I've found. There exists a number delta where I can do this. And I can do it no matter how small epsilon is. You want to think of this number right there as being L plus epsilon, in this case 1 plus epsilon, and this number here as being L minus epsilon, in this case 1 minus epsilon. If you do that, then this distance right here and this distance right there are both epsilon. Let's use a different color here. That distance right there is epsilon. This distance right here is epsilon. Epsilon, you can see I've drawn it as fairly small, but I could draw it even smaller. I could make these points even closer to 1. No matter how small epsilon is, because the limit truly is 1, I'm going to be able to find a small number delta, a sufficiently small number delta, so that if x is within a distance of delta to 3, c is 3, then the outputs of the function are within epsilon of 1. How small would delta have to be visually in this picture? it would have to be smaller than this distance right there, between 3 and this point that is right below that intersection point right there. So take it smaller, maybe like this small. Pretend that number is 3 minus delta, and the corresponding number over here is 3 plus delta. I didn't draw it very well. Let's see. Yeah, I need to make delta smaller because I didn't draw it very well. The line is a little bit more like this. Let me make it even smaller, so that this point is closer to that. And this distance here, trying to make very small drawings, that's delta, and this is delta. And if x is within delta units of 3, if it's inside this little interval, then the function outputs, the second coordinates of points on the graph, are going to be within epsilon of 1. Okay? And because the limit truly is 1, that'll work no matter how small delta is. And if I thought for some strange reason that the limit was something else, like 2, up here, say, then I would not be able to get arbitrarily close to 2, even by taking x really close to 3, because the function value doesn't get close to 2. And that would work even if I picked 1.1 or 1.01 or 1.0001. You'd be able to pick a really small epsilon where you would not be able to get within epsilon of that incorrect limit. This is not easy. This is hard. Okay? All right, now let's go ahead and do the proof. So I've got to use this definition to do the proof. Now, for sake of time, I'm not going to do scratch work, or at least not full scratch work. But you should realize that when doing proofs like this, you almost always have to do some problem-solving scratch work. Okay, it's not really possible, except if you got a lot of experience, to do these proofs without doing some scratch work. Here's the structure of how you do the proof. You start by saying, give me an arbitrary positive number epsilon. Let epsilon greater than 0 be given. In fact, I had a teacher who told me, think of it as a stamp. You're stamping that down as the very first thing you always say. And now I tell my students that too. Let epsilon greater than 0 be given. Epsilon could be big, but in your mind you're pretending it's small. It's sort of more relevant when you imagine it's small. We got to choose a delta. We need to show there exists a delta so that this clause is true. That's the hardest part. How do you choose delta? It is going to be a positive number. It's got to be related to epsilon. I mean, the smaller epsilon is, the smaller delta needs to be. How small should it be? With linear functions like this, the answer is to let delta be epsilon divided by the slope, or the absolute value of the slope if the slope is negative. Slope is 2 here. Let delta be epsilon over 2, which is a positive number. We do want delta to be positive. So I'm choosing, I'm trying to show there exists a delta, so I'm choosing a delta. And this is going to work. Now, so this is always the hard part. And this is what the goal of your scratch work should be, is to figure out what delta is. If it's a nonlinear function, even like x squared, it gets harder. And what you often have to do is you often have to let delta be still related to epsilon, but like to be the minimum of epsilon over 2 or something, and maybe 1 just to make it easier to handle. Some tricky stuff goes on with factoring and thinking about something called the triangle inequality, and I don't want to get into it in this first example of a limit proof. All right, well, what do we need to do with this? We need to show that this clause is satisfied. Assume x satisfies this and show that f of x satisfies this. Assume that we have chosen x so that 0 is less than the absolute value of x minus c, c is 3, is less than delta, which is epsilon over 2. We're going to assume that. We want to show that this implies that. So assume this. We've got to show this. How? Well, just start working with the left side and see if you can show it's less than the right side. See if that happens. Will that happen? Then the absolute value of f of x minus L, f of x is 2x minus 5, and the L is 1. Simplify it. That's the absolute value of 2x minus 6. We need to use our assumption somehow. How do we do that? How do we use that assumption? Well, if you factor out a 2, lo and behold, you're left with an x minus 3. Hey, there's an x minus 3 there. The absolute value of the product of two numbers is the product of their individual absolute values. The absolute value of 2 is 2. So we have 2 times the absolute value of x minus 3. What do we want to do with this? We want to show it's less than epsilon. The assumption, again, is relevant. We're assuming this is less than epsilon over 2. Done. How about that? I never actually had to use the assumption that x was not equal to 3 here. There are some situations where you do have to use the assumption. I went ahead and wrote it anyway. We're done. We showed it's less than epsilon. Wow. Are we really done? Is that what we're supposed to do? QED? It is. And you really are done. We showed that for any arbitrary epsilon, I can choose a delta, so that if this is true, then this is less than epsilon. Exactly what the definition says to do. It kind of feels like we didn't really do much, but you really did. You really proved it. This is the easiest kind of problem. Things get harder from here, but it is a worthwhile subject to study, mostly because it allows you to prove general theorems that can apply in more situations where you maybe don't have to do this. It is a worthwhile thing to study. Thanks for watching.